Hello everyone, welcome to 16th lecture in this series of remote sensing, and in this particular lecture we will be discussing image classification techniques. There are various types of image classification techniques exist, and some are also evolving. So few of them we will see which are most popular. But before that we would like to focus why we want to classify. As you know that image is a continuous data. It is not discrete data like a simple map, say maybe a land use map or a lithological map or soil map, where the boundaries are distinct and one unit is there for one soil, one type of soil another, and within one unit you do not have the variations, but an image is a continuous data, not a discrete data. So sometimes it becomes very difficult to use continuous data, and therefore from continuous to discrete, one way of doing this thing is to perform image classification. Ultimately what we try to go for image classification to say for a lithological mapping, for maybe for mineral exploration, maybe for alteration mapping to find mineral deposits, or a very popular application of image classification, that is land use and land cover, LULC in brief we mention, maybe for vegetation types, maybe based on density, maybe based on the species type. Similarly in agricultural fields also, we also use image classification to show different types of crops, their conditions and so on. So basically any image can be classified, can be discretized into certain number of classes as per our requirements and the variability which exists within an image. So this is not an exhaustive list, it is a everyday new applications and new classification techniques are. So if we look the different types of classification here, basically as I have mentioned that we would like to convert that continuous remote sensing data into discrete form, and so that we get some meaningful categories representing surface condition or classes. Also some people call as instead of image classification they call as feature extraction. Also some little different terms are also used like pattern recognition. So there are three types of these recognitions. First is spectral pattern recognition, and the procedures classify a pixel based on its pattern of radiance measurement in the each band, more common and easy to use, this spectral pattern recognition. Then the second one is the spatial pattern recognition, in which under this the classification is based on though it's a pixel, but it's relationship with surrounding pixels. In the previous one each pixel will be treated independently, but here the surrounding pixels, neighboring pixels are also considered. So this one is more complex as compared to spectral classification, more complex and difficult to implement. And the third type is the temporal pattern recognition. This is becoming more popular nowadays because of a lot of data through archives. So it looks at changes in pixel over time to assist in feature recognition. So if you are having a time series data, you want to classify, you want to create some maps which can tell lot many things, meaningful feature or extract meaningful features, then temporal pattern recognitions are possible. Now different types of classification that was based on the pixel, neighboring pixels, or in the change detection, but the other way most popular one which you would find in the books of remote sensing or digital image processing is especially these two types. One is unsupervised classification, which we will take little later, which is very simple one and popular one as well, and supervised classification which requires certain inputs by the user, so that it involves a lot of work, and therefore it is more accurate, and people use both types of this one. Now in unsupervised classification, basically what we do, instead of a continuous data, we aggregate this continuous data into natural spectral groupings or clusters based on their spectral radiance. and no knowledge of about thematic cover class. When we perform supervised classification, we don't have basically the ground information much available. Whatever we are seeing on the images, based on the spectral radiance, based on the spectral characteristics, one can classify under this unsupervised classification. Not many inputs are required, except that if suppose I am having an image, I want to instruct the computer or the software that please classify in 8 classes. So based on their spectral variance, the 8 classes will be generated. But these maps, though it is one of the very popular way of doing classification, but still it is having lot of limitations, and they are not that accurate either. But in supervised classification, which is we identify certain areas, that this is per my interpretation skill, this is the forest area. So consider the spectral characteristics of this area and implement this throughout the image. Wherever the similar characteristics, spectral characteristics exist, then consider this as a forest cover. And if I choose another area like bare soil or bare rocks or sand bodies, water bodies, so similarly I train the software or train the system to classify images according to the spectral characteristics available there. So we will see here, and that pixel look like most based on that training set pixels categorization, and because this is being supervised by an user who is going to do classification, that is why it is called supervised classification. Training set or areas are used as a numerical interpretation keys. So this is how that if I am having a say false color composite of an area, and I am having some skill of identifying different ground features, then I will train the system that as per my understanding, this is water body, this is bare soil, rock, forest, agricultural land, and sand part and other things. Like here in this example, that water, sand, forest, urban, and cornfield, hayfield, and all these things are there as per their pixel values in different bands. These training sets will instruct to classify this image, this color composite or different bands. So likewise ultimately I will have. So first step in this basic step in supervised classification is to train. That is training stage, collect numerical data, that is means pixel values from different bands, from training areas where I am sure that this is say dense forest. So I will select from there, collect the training area, and then depending on the spectral response patterns of land cover categories. And then second stage is classification stage, compare each unknown pixel to spectral patterns assigned to the most similar categories. So wherever the computer will find the similar spectral characteristics, that area will get for forest and so on and so forth. Better the training we give to the system, better the classification we can achieve. So here the input from user are very important, and then in here once these classes have been compared, the training sets have been compared with the remaining spectral patterns, then the classification is achieved, and then in output stage you will have a map. Like if I have classified this band and then image, a color composite image using these number of classes, I will have a map, maybe a land use map, forest density map, lithological map, maybe soil map, and so on. So likewise I will have a map, I will have table of areas which will tell us the statistics, that how much different categories are covering, what are their percentages, and will create the digital files so that we can use elsewhere. So training stage is very important, and that determines the success of classification. If training sets are very reliable, and if user is having prior information about that area, then it becomes very good. If it is not, then if I have to do a very accurate classification, then one has to go in the field, really check whether the area which I am identifying as a dense forest is really exist in the field or not. So likewise, if I have collected field data or training sets from the field and then I input in the image, then my classification is going to be very accurate. So classification stage, which is the heart of the supervised classification, and the output. So three stages are there. Now spectral characteristics, which we have seen some spectral curves for different types of ground features like vegetation, water, bare soil and all those things. So now that understanding will really play a very important role. Like here, one way of looking is through this this graph, like I am having different bends here, or plotting against this EM spectrum and number of pixels. So what I find that for water there is one curve, for land there is another curve, vegetation and other thing. So I can distinguish this. The other way, instead of doing this thing, I can go for a 2D scatter plot, and if I may get clustering of pixels like this. So then I can train, after looking such scatter plots, I can train my image for classification in a much better way. But if I am having the facilities to go for 3-dimensional plotting, then my, like here, the red areas, which is the vegetation in this schematic, and the bare soils. So there is some overlap in 2D, in 2-dimensional space I am seeing. But in fact they are altogether different, there is no overlap. So here in the 2D there is a overlap, but in 3D I can discriminate very easily. So I can train to my software that this area where in these two bends or in three bends, this is the characteristics of water body, these are the spectral characteristics of vegetation, this is the characteristics of urban area and or built up area, this is the characteristics of water, and likewise then I can classify more reliably. So instead of 1-dimensional image histogram, we generally we prefer a 3-dimensional histogram, or even in sometimes a 2-dimensional histogram or a scatter plot can serve our purpose. But the best thing, whatever is available, if we plot here, then we can discriminate different features based on 3 bends characteristics, and generally like we perform on a color composite. So their 3 bends will have their plottings, spectral characteristics, and then classification can be done. So better, as have been mentioned, that better we train the system, better for the cases where validity of classification depends on a priori knowledge of the technician or whoever the user who is going to classify the image. So if we are having some ground information about that area, then it is going to be much better way. And conventional cover classes are recognized in the scene from prior knowledge. After certain experience, one becomes expert on interpretations, image interpretations, and therefore one can train the system very easily about different classes, and training sets for each class are chosen. Then each training site, that is class, results in a cloud of points in a n-dimensional, as I have shown, in a 3-dimensional space, and then you assign different colors just to represent different classes. Maybe like for vegetation you may assign green color, for water body you may assign blue color, and so on and so forth. Like here, this is a real example that the main aim is to classify this image as per the land use or land cover type. These two terms are used, land use and land cover. Land use, when we use land use word when human interventions are prevailing in that area or prevalent in that area. But land cover, we use the word when we feel that it's a natural terrain, not much human interventions are there in that area, then we use the word land cover instead of land use. So in this one, in the land cover analysis, these are the different training sites have been identified. How these have been done as explained, like if there is a forest and different types of even green patches which you are seeing, these are the training sites. So like this light green color, which is this area. So based on image interpretation or might be priori knowledge about the area, I am sure that this area is having trees, big trees. So this area has been this much spectral characteristics have been collected and assigned a color and declaring to the system that wherever you find the similar characteristics, spectral characteristics within that image, classify it as a trees. Similarly for water bodies or sea water, like for sea water, so this area it is found that okay, this is good training set for the water or sea water. So wherever the spectral characteristics will match within this image, that entire area will be classified as sea water. Maybe for sediments, different types of concentration of sediments which is visible can be classified, urban areas and so on and so forth. And once these training sets have been collected, then rest of the thing has to be expanded in the entire image by the computer or by the software, that wherever these similar characteristics for each classes will be matched, those areas will be assigned the same color, and then you get the result, which we will see little later. So after the training sets, the next step is for the computer to assign each class to spectral class is appears to belong to based on the digital numbers or pixel values of the bands which are being used. And clustering algorithms looks at clouds of pixels in spectral measurement space, that is in 3D space, from the training to determine the cloud or the clustering for a given training samples. Likewise here, if this is schematic, not exact of this image, but just for explanation, that here these are the like this is this color is indicating that these areas have been cleared off. So they are having different spectral characteristics. This area wave surf areas which are having like this one having different characteristics, and these clusters in 3D space can be seen. So once it is done, then algorithm is used. Different algorithms are there which we will discuss one by one. The first one, the very popular one, is the minimum distance to means classification, also called the chain method. Another one is the Gaussian maximum likelihood classification or classifier, parallel piped classification, and each will give a slightly different results, and we will see some results and compare how they create different outputs. The simplest method is, as I have mentioned, is the minimum distance, in which a theoretical center point for each cluster is plotted based on the mean values, and an unknown point is assigned to the nearest of these, and the point is then assigned to that class. So all these here first minimum distance to mean. So for each class, as mentioned, for each cluster there will be a mean, and for entire there will be a mean. So this is minimum distance to mean, that is the area and the distances are measured, and then clusters are decided that these pixels belong to a particular class. Here in this schematic, these like these plus symbols are belonging to the R1 class, and so on and so forth. So this way, if we go for classification, use that algorithm after training sets, that is the minimum distance to mean. Then there is a parallel piped classification, or where instead of determining the mean, a box are drawn, and wherever these pixels are falling, having the same spectral characteristics, accordingly they are assigned. As you can realize that here the plotting is same in 2D space, plotting is same like here, but I can draw a box so that some more pixels will be included of some other areas, but if I draw a circle or a maximum likelihood, then I will have a altogether different, and therefore there will be some difference in the results. More precise, instead of simple parallel piped classification where only the rectangles or squares are drawn, I can draw some other types of boundaries and can have more precise parallel piped based algorithm based classification. So different methods of spectral classification can be represented diagrammatically, as here I have just shown, and this is another is maximum likelihood classification, the third type, that the contours here the contours are drawn, and these are based on the probability, that the contours express the probability that any point belongs to a particular class, which is basis of maximum likelihood method classification. And likewise that the center of this cluster of having plus symbols is having the maximum likelihood. As you go away, then that likelihood intensity decreases, and there might be some mixed pixels scenario as well, that whether those pixels can be classified at one type of land cover or another type. So these mixed scenarios might be there in certain areas. So if like two examples are given, one is minimum distance classification based on the training sets which we have discussed earlier, then this is how the output map, that is land cover map, will look. But instead of using a different algorithm, rather than minimum distance classification, a maximum likelihood which is based on the probability, then this is how the map will look. So at several places there are some changes one can notice, especially like these shadows areas in this one are much more in maximum likelihood, which have been classified, here less. And maybe about these areas, this is the marshy land which is less classified here, but more uniform classification has been done. Now how to judge that which one is the better? So again, one has, if one wants to really check that which one out of these three, four algorithm based classification is giving better results, then it is always good to go again in the field and check whether it is the same way it has been classified, or there are some spectral or there are some mismatches, and then one can come back again and correct it. So in this way the classification accuracies can be improved. Now initially we put in two categories, one is unsupervised classification and supervised. Supervised we have discussed. Now we come to the unsupervised classification, which is completely a software based or computer based classification. Our input is required whether we want to classify that map or that satellite image in 8 classes, 7 classes, 5 classes. Now this input will come through our image interpretation skill, that we interpret the image and find that there are a major 8 classes, suppose. So then we will assign to the computer that classify this image based on the 8 categories of different land cover. So but the concept wise same, that you can think that in 3D these are the plots. Then initially we assign spectral class 1, spectral class 2, that means the clustering of the pixel values in a 3D space, and based on that then later on you can assign different clusters or different colors ultimately, which will come to different category of land cover. So here the basic assumption that we do not have any prior knowledge about the area. So local information is not available, and so computer, what the software will do, it will group all pixels according to their spectral relationships and look for natural clustering. So wherever it will find the cluster, it may assign one class. Now you have to identify whether the class it has assigned is a water body or not, and in natural convention we will assign blue color to the water body. So in this way we achieve unsupervised classification. So here assumes that the data in different cover class will not belong to the same grouping, and once created, once we have given this to the computer, the analyst then later on assesses the utility and can adjust clustering parameters. So later on, once we realize that water body is being, or bare soil is being classified along with the sand bodies, but then some adjustment or accuracy can be introduced if I am sure that computer is wrongly classifying. So based on their spectral characteristics, these things can be adjusted later. So after when this comparison is done, the reclassified image based on the spectral classes to ground reference data. The analyst can determine which land cover type the spectral class correspond to, and has the advantage over this technique. Unsupervised classification is having advantage over supervised, because here it is done by the computer. So sometimes we might be in supervised classification, we might be choosing a wrong area as a training site. Training site has to be very exclusive area, and we are sure that this is definitely a dense forest or a bare soil or bare rocks or water body, sand body, then only we should assign. So we are introducing a bias to the system. But in case of unsupervised classification, we are at initial stage, no bias is being introduced, except that we are giving number of classes so that image can be classified. But both types of classifications are having their advantages and disadvantages. And this clustering algorithms in unsupervised classification includes like k-means, textural classification and other things. This is the same image was subjected to the same number of 15 number of classes. These are the clusters. Now like if I realize that this is the seawater, so instead of mentioning a cluster, I will just put remove this and I will put a seawater. And similarly, if I find this color is showing the high sediment concentration, then I will say the turbidity or high sediment concentration. If I find that this is a water body, then I will assign is a lake water or whatever. If I find that the green color is the forest area, then I will. And how I will find? Very simple. You will have one classified image and same time you will have a color composite. So by comparing that one, you can assign to these different clusters different classes. You may merge, you might realize. So initially what we do in case of unsupervised classification, the best practice is to classify in more number of classes than you think. Say I realize that probably there might be only 8 classes. So first I will instruct the system to classify in 12 classes. Then I can do the grouping as well, and that will make sometimes this iteration makes the classification results much better. There is another simple unsupervised classification technique on a single band if we perform, or maybe in a color composite it can be performed, which is called slicing or density slicing. Generally it is performed on a single band, that is why gray levels or digital numbers distributed along x-axis of an image histogram are divided into a series of analyst specified interval or slices. So it is something like you are having a loaf of bread. Now you want to classify on equal thickness of slices of the bread, or maybe depending on the distribution, that means the histogram based on the frequency, you want to classify or make the different thickness of the bread as per the requirement. So all DN and digital numbers, pixel values falling within a given interval are displayed as a single DN, that means a different color in the output image, and the process of converting the continuous gray tone to an image into a series of density intervals or slices which each correspond to say specified in specific digital image. Like for example here, that pixel values within one band 6 example here, or that pixel values within 0 to 15 should be assigned red color, 16 to 32 should be assigned 32 green color, and so on and so forth. So again this is a simple discretization. Instead of having a continuous image, the same image is being classified based on, so this distribution of or the thickness or the width may be different depending on your requirements, or you may involve some statistical techniques like equal interval or natural breaks or quantile. There are many such methods are available which can be used to classify a single band image. There are some other classification techniques are evolving recent times they have become popular, which are pixel based. So we compare with this object oriented classification versus pixel based classification. So far what we have been discussing is pixel based. Now so we can improve on this. In the past, most digital image classification were based on the processing the entire scene pixel by pixel. So instead of now we may think about identifying the objects and then going for classification. So object oriented classification techniques allow the analyst to decompose the scene into many relatively homogeneous image objects referred as patches or segments using a multi-resolution image segmentation process. So this brings to the end of this presentation. Thank you very much.